Using identities to solve equations, and specifically trigonometric equations. Today is actually the 13th. So we are also going to look at how we use our identities, starting off with our main identity, sine squared theta plus cos squared theta being equal to 1, and the various ways we can manipulate that. Let's look at this first example here. We're asked to find values of theta in this interval here that satisfy this equation. So like with the previous equations, we can see if we need to deal with the power, it might be square rooting to find a singular or more than one value for which satisfies the ratio. We might need to look at a hidden quadratic, or we might need to factorize, making a special note that when factorizing, it's nice to have the subject being equal to 0, where each of the factors could be 0, so that we can solve. We saw yesterday that it wasn't helpful when it was equal to something other than 0. So here it looks very similar in the first instance to a hidden quadratic. However, it's two different ratios. I've got sine here and cos here. However, we recognize that from our main identity, sine squared theta plus cos squared theta is equal to 1, that I can say that sine squared theta is equal to 1 minus cos squared theta. Therefore, all instances of sine can be replaced with 1 minus cos squared theta, as they have it in this example here. And now we can complete it in the way that we did some yesterday. So we can manipulate it to expand brackets here and here, get more values to one side, and we end up with our quadratic, which is actually 2. If I say cos theta is equal to y, I've got 2y squared minus 3y minus 1 is equal to 0. Solve for y values of this and this, and now we can go forward. Just like one example yesterday, remembering that both cos and sine have maximum min values of +1 and -1. So if I ever get one value which is greater than those, a value which is greater than those, I can simply reject this and work with the other value and go from there. So in this case here, we've seen that we're going to be working with cos theta is equal to -0.281. So for that value here, and the range we were given, because it's in terms of theta, I don't have to worry about extending or shrinking the range. It's going to be between -180 and 180, and I can see that I'm going to get two values between that range, here and here, for my values of theta. So plunking cos to -1 of -0.281 in the calculator, the first value you get out is this one, and because it's symmetrical, you're going to get this one, giving you your two solutions here. Okay, let's look at another instance here. So we're asked to solve this example here. Now we start off with two different ratios, sine theta and cos theta here, and as we said yesterday, we're going to try to avoid dividing by sine, because that's going to that could cause some problems. But we can actually, in this case, divide both sides by cos, theta, beg your pardon, and end up with this being equal to -3, and we know sine over cos is equal to tan. So we've got this. So all we need between this interval of -360 to 360 from here and here, where I meet up with -√3, I'm going to have 1, 2, 3, 4 points of intersection, giving me my 1, 2, 3, 4 solutions. Your calculator will give you this first one here, and you can simply just add 180 to get to the next one along, hopefully staying within the range you've been given. Notice this one will go beyond the range, so we go backwards, taking away 180, and you should get the following solution. So your first one was negative, add 180, this one here, and then you've got your 4 solutions. Then again, a quick check to look at your range to make sure all of your solutions are within that range. Let's look at this next example. Now, you have an expression which looks quite tricky because it's now 2x inside your ratios, noticing your intervals being given in terms of x instead of 2x, so you're going to need to think about dealing with that. If it helps with your juggling, you may want to turn 2x into a straight away, but remember how you're going to be dealing with that. So first of all, a little bit of manipulation. Here you can recognize that tan can be written as sine 2x over cos 2x, okay, and that's what they've got here. So split it up, and now they've multiplied both sides by cos, which gives us this situation here, and now they have brought all values to one side, allowing us to factor. So either this part is equal to 0 or this part is equal to 0. So they've set it up here below, that being equal to 0 or that being equal to 0. I'm going to work with them separately. In the first instance, let's look at this. So when this is equal to 0, I'm going to actually work with letting 2x be equal to a for now, just so it's easier to work with, and we can undo that later on, but bring it back later on. So we need to think about interval. Here we're given an interval in terms of x, we want 2x, so we're going to have to double all parts of my inequality. So 0 times 2 is 0, 180 times 2 is 360. Therefore I get this new interval to work with. So a between here for sine, it's going to be between 0 and 360. That's my interval. And for 0 is just going to give you that value, and that value. So you get 3 solutions for that. And now I know that 2x is equal to a, so I need to divide all these solutions by 2, giving me 0, 90, 180 degrees. Now for the second part of that, a little bit of manipulation is needed. I need to add 1 to both sides and then divide by 4, so I get cos of a is equal to a quarter this time. So I'm still working with the same interval because it's still for 2x. Now, again, between 0 and 360, I'm expecting 2 solutions for a positive quarter here and here. Into your calculator, inverse cos of 1 quarter gives you 75.5 as your first solution, and you know it's symmetrical, so 75.5 degrees away from 360 is going to be 360 degrees. Take away 75.5, giving you your second solution here. Now remember, these are 2x and you want x, so you're going to have to take each of these values and divide them by 2, giving you this value and this value, and you add them to the ones we had. So in total you have first 3 solutions here, the next 2, 5 solutions in total.